So let us begin at the beginning. What is the real story behind Ptolemy, Copernicus, Galileo, Newton, Einstein, and the rest? What secrets lay hidden until now of the lives and thoughts of these icons of the modern world? As we shall see, everything is not as it seems. Nicholas Copernicus was a canon of the Catholic Church. He published a book around 1510 titled the COPERNICUS, advocating the heliocentric system, in which the Earth revolves around the stationary Sun. At the request of the Pope to fix the Julian calendar, a calendar which was increasingly becoming inaccurate as the centuries went by, Copernicus believed that his heliocentric system might be a more accurate timekeeper. By 1543, the year of his death, Copernicus finally published his second and more advanced book on heliocentrism titled De Revolutionibus Orbium Coelestium. Under advisement from his Lutheran counsel, Andreas Osiander, Copernicus presented his book to the Pope only as a hypothesis, not as a thesis or fact. There are two important things we should know about Copernicus's heliocentric system. First, in spite of the fact that Copernicus's name is often attached to the system in which the Earth revolves around the Sun, Copernicus was not its originator. It first appeared in the Greek school of Pythagoras around the 6th century BC, which was later advanced by its chief proponent, Aristarchus of Samos, in the 3rd century BC. Copernicus was merely trying to revive this ancient system. Other Greeks, such as Aristotle and Hipparchus, were devoted to the geocentric model.
The second important fact is, although Copernicus rejected Aristotle's geocentrism, he nevertheless believed in Aristotle's philosophy, especially that the circle was the perfection of shape and movement. Therefore, Copernicus sought to put the planets in uniform orbits, and do so by having them move through perfectly circular crystal tubes.
Here we see a page taken from Copernicus's book, De Revolutionibus. It shows that he wrote the name of the planet inside each circle to represent Aristotle's original model that the planets were traveling in circular and transparent crystal tubes. Since today we know that the planets neither travel in tubes nor revolve in perfect circles, it is no surprise that Copernicus never succeeded in getting his model to work correctly. Copernicus tried to compensate for these difficulties by adding more movements to the planets. To do so, he added more circular paths to his original circles to make the movements of the planets more versatile and flexible. But even this remedy did not produce an accurate representation of what actually occurs as the planets move in the sky. As a result, Copernicus's model was more or less a failure, since it charted the planets' movements no better than its forebearer, Aristarchus. Copernicus's system was also no more accurate than its geocentric rival, the Ptolemaic system, which had been developed by Claudius Ptolemy in the 2nd century AD and had been the reigning model of cosmology for the 1200 years prior to Copernicus. In fact, to bring his model close to the accuracy of Ptolemy's, Copernicus was forced to add more circles to his model than Ptolemy had in his model. Today we know these extra circles as epicycles, from the Greek word epi, which means upon, and cycle, which refers to a circle. In his first book, the COPERNICUS, published in 1510, Copernicus was already forced to use 34 epicycles. By the time he published his final book in 1543, he realized that the motions of the planets were much more complex, and thus he was forced to add 14 more epicycles for a grand total of 48 epicycles, which was 8 more than Ptolemy's model. Ptolemy understood that the Greek cosmological models, whether the heliocentric of Aristarchus or the geocentric of Aristotle, were rudimentary, and thus could only provide general movements of the planets. Ptolemy discovered that planetary motions were much more complex than what circles could represent. To compensate for this difficulty, Ptolemy invented 2 geometric devices. The first, as we have seen, was the epicycle, which even Copernicus himself used for his heliocentric model. Ptolemy's second invention, which was the greatest achievement of astronomy in the first millennium, was the equant. The equant allowed the planets to move in non-uniform orbits so that the speed of the planet could vary. In fact, as we shall see, Ptolemy's equant-based orbits were the forerunner of Kepler's elliptical-based orbits. Both artifices accomplished the same purpose, creating non-uniform orbits for the planets to match their erratic movements in the sky. The problem with Ptolemy's model, however, is that it was not equipped with accurate distances between the Sun and some of the planets. As a result, Ptolemy placed Mercury and Venus in the wrong position relative to the Sun, and Galileo later noticed this problem when he saw the full phases of Venus through his telescope. Full phases, which Ptolemy's model could not produce. Ptolemy was quite clever, however. He left 6 variables so that in the future his model could be adjusted when the correct distances became known. Although Copernicus, as we noted, had problems of a different nature, still, he did not need to know the exact distances to the planets. His model only required him to know the order of the planetary orbits, and for the heliocentric system, this was known since ancient times. As a result, Copernicus's model had no problem showing Venus's full phases. This was one of the reasons Galileo promoted Copernicus's model as being superior to Ptolemy's. Galileo reacted against Ptolemy for another reason. Ptolemy's model had the Sun, which was known to be larger than the Earth, revolving around the smaller Earth. To Galileo, this seemed counterintuitive, especially since he had witnessed in his telescope that small moons were revolving around the larger Jupiter. Galileo believed that the smaller Earth should be revolving around the larger Sun. This was a lingering objection to the geocentric model. We will see the outcome momentarily. A major development occurred for the heliocentric system that made a vast improvement over the crude and unworkable model of Copernicus. In order to account for the irregular movement of the planets, Johannes Kepler dispensed with Copernicus's circular orbits and instead put the orbits of the planets in ellipses. This adjustment allowed the planets to travel at non-uniform speed, just as Ptolemy had accomplished with his equant a millennia and a half earlier for the geocentric system. The planet orbited in an ellipse around 2 foci, with the Sun occupying one of the foci. So instead of using Ptolemy's equant, Kepler made the Sun one of the 2 focal points around which the planet would revolve. The result was that when the planet was closer to the Sun, the faster was the speed of its orbit. The farther away, the slower the orbit. So close were Kepler's ellipses to that of Ptolemy's circle with an equant that we can superimpose one on the other and see the similarity.
In the battle of which system was correct, the heliocentric or the geocentric, Tycho Brahe, the famous Danish astronomer, presented a perfected model of the geocentric system. Tycho did 2 basic things. First, he inverted the Copernican model. Although he still allowed the planets to revolve around the Sun, he made the Sun revolve around a fixed Earth. As such, the Earth was no longer a planet.
In this way, the Tychonic model kept the geometry and distances that Copernicus had employed. The only difference was that the Earth was the center of the whole system instead of the Sun. By doing so, Tycho also corrected the Ptolemaic model, since Mercury and Venus were now at their correct positions from the Sun. As we can see from the animation depicting the orbit of Mars, the distances and relative movements of the 3 systems are equivalent. Although Tycho's model did not use either elliptical orbits or an equant, if such a modification had been applied, it would have made his model just as accurate as Kepler's. As one physics course from the University of Illinois put it, quote, "One could also construct a Tychonian model with elliptical orbits," unquote. This modification was, in fact, added to Tycho's model by Giovanni Riccioli in his 1665 book, Astronomia Reformata. And after Riccioli made this modification, he remained a devoted geocentrist. For reasons that were more philosophical than scientific, Kepler did not want to promote Tycho's new geocentric model. Kepler highly valued the Sun as the centerpiece of the cosmos, whereas Tycho sought to preserve the ancient astronomy from Ptolemy that had the Earth in the dominant position. As is often the case in science, one's philosophical views invariably influence his interpretations of the scientific data. Hence, after Tycho died, Kepler made arrangements to obtain Tycho's 40 years of planet charting that was originally meant to support the geocentric system, and he used it for the heliocentric system. This wasn't hard to do, since, as we have seen, the models were geometrically and mathematically equivalent. As world-renowned physicist George F.R. Ellis notes,
"I can construct for you a spherically symmetrical universe with Earth at its center, and you cannot disprove it based on observations. You can only exclude it on philosophical grounds. In my view, there is absolutely nothing wrong in that. What I want to bring into the open is the fact that we are using philosophical criteria in choosing our models. A lot of cosmology tries to hide that."
Following Kepler, Galileo also rejected Tycho's model. Perhaps this was because in Tycho's model, the large sun was revolving around a small Earth, the opposite of what Galileo intuited when he saw moons revolving around Jupiter. About a century after Kepler, Tycho, Galileo, and Riccioli had battled against one another, Isaac Newton arrived on the scene. In his book, Principia Mathematica, he published his now famous 3 laws of motion. As fate would have it, Galileo's intuition about smaller bodies revolving around larger bodies was confirmed and put into a mathematical equation by Newton. Newton's equation said that the force of movement is determined by the mass of an object multiplied by its acceleration. It now seemed that heliocentrism had finally won the great battle of cosmology. Newton also said that the force of gravity is equal to the mass of the first object multiplied by the mass of the second object divided by the square of the distance between them. Since the Sun is more massive than the Earth, the gravity of the Sun is greater, and thus would pull the Earth toward the Sun. To compensate for the inward force of acceleration toward the Sun, the Earth must produce an equal and opposite acceleration away from the Sun in order to stay in its orbit. In the heliocentric system, the acceleration is produced by the Earth's circular motion, and the Earth is said to continue the acceleration by inertia. Simply put, Newton said the Earth seeks to move in a straight line, but the gravity of the Sun keeps pulling it inward, and the result is the Earth's circular movement around the Sun. Newton made a crucial distinction, however. He added that, strictly speaking, the Earth does not revolve around the Sun, but both the Sun and the Earth revolve around a mutual center of gravity or center of mass. But since the center of gravity is closer to the Sun, then for all practical purposes one can say the Earth revolves around the Sun. At least it seemed so to Newton and the people of his day.
The fact that there would be a center of mass between the Sun and the Earth seemed to be the clinching argument to settle the heliocentric versus geocentric debate. Since Newton's equation, F equals ma, could be demonstrated and measured in the laboratory, there was little opposition the geocentric position could mount, except to rely on their theological and philosophical convictions and hope that science would gain more knowledge later to confirm those convictions.
Great names from the Enlightenment age, such as Immanuel Kant, who was called the father of modern cosmology, sided with the heliocentric view based on Newton's laws, as did many other famous scientists of that day. Although Kant had theorized about the existence of what he called island universes composed of thousands of stars, at this point in history no one knew much about the stars, except that they shined as points of light in the sky around the Earth. No one knew how big they were, how far away they were, how many there were, or what influence they might have on the question of geocentrism and heliocentrism. By the mid-19th century, however, physicist Ernst Mach and his colleagues proposed that the stars are as big or bigger than the Sun. Telescope observations showed that the number of stars in the universe was enormous, filling every quadrant of the sky. Mach reasoned that since the Sun, because of its large mass, has a great force of gravity, the stars must also have a corresponding gravity, and thus their combined gravity would greatly influence any region of the universe, including ours. Hence, Mach, in opposition to Newton, argued that no place or object in our solar system escapes the force of the stars. Whereas Newton believed the Earth revolved around the Sun against a background of a fixed but empty, absolute, and immovable space of which the stars did not contribute any force, Mach argued that space was permeated by the gravity of the stars. In a word, whereas Newton believed in absolute space, Mach introduced the concept of an absolute gravity. Hence, Mach argued that not space, but matter, which produces gravitational force such as what we find in the stars, should serve as the fixed background to measure any terrestrial or celestial movement. For example, Mach said that the reason we will be pressed against the wall of a rotating amusement ride is that the gravitational force of the stars surrounds us. We feel the stars' ubiquitous force whenever we change direction or accelerate on Earth. Otherwise, we are oblivious to it. A rotating amusement ride, although it moves at a uniform speed, is understood to be accelerating in physical science, and thus we feel the force, otherwise known as centrifugal force. As one modern scientist put it, quote, "When the subway jerks, it's the fixed stars that throw you down," unquote. What this means is that there is a gravitational tension on Earth created by all the masses of the universe, tension analogous to a stretched rubber band. When we suddenly move against that tension, we feel it as a pushing or pulling force on our bodies. This is otherwise known as inertia. Conversely, Newton argued that our body wants to move in a straight line in absolute space, instead of a curved path, and thus always seeks to break off of a spinning carousel. As we can see, Newton's and Mach's ideas about the concepts of force and movement were very different, to be sure. Additionally, Mach's new insight of the universe led him to conclude that there was no difference between the Earth rotating in a fixed star field as opposed to the star field rotating around a fixed Earth. Both systems would produce the identical forces. Consequently, Mach's contribution to science reopened the heliocentric versus geocentric debate. If there was no difference between a rotating Earth and a fixed star field, as opposed to a rotating star field around a fixed Earth, how could we determine which was the reality? In a word, Mach expanded our view of motion beyond the two-body mechanics of Newton's original equation. If m1 is the Sun and m2 is the Earth, Mach said, in a roundabout way, that we needed another m to represent the stars. Newton's laws of motion could still be applied in closed systems in which a limited number of bodies were present, say for example, the moons of Jupiter going around Jupiter. On much larger scales, however, that is, the scale of the universe itself, how would Newton's laws of motion apply if the whole star field were in rotation around one central point, and that point happened to be the Earth itself?
The answer is very simple. According to Newton's laws, if the universe's stars were rotating around a fixed Earth, the center of gravity, or center of mass, would no longer be near the Sun, but at the Earth itself. Theoretically, the universe could be positioned in such a way that it would balance perfectly on the Earth, and thus keep the Sun a safe distance from the Earth. The Earth would act as a center of mass for the universe.
Essentially, the whole universe can rotate around a motionless Earth and obey the laws of physics as they are presently believed to function in both Newtonian and Machian mechanics. Although Newton sought to apply his laws of motion only to the solar system so that, as he says in his 1684 scholium,
"Hence indeed the Copernican system is proved a priori, or if a common center of gravity is computed for any position of the planets, it either lies in the body of the Sun or will always be very near it."
In the end, Newton realized, especially after consultation with Christian Huygens, that his laws of motion could be applied more expansively. In doing so, it would allow the solar system's center of mass to be near the Sun, but also allow the Earth to be the center of mass of a much larger system. As such, the Sun, with its planets, would revolve around a fixed Earth as described in the Tychonian system. For this alternative to be permitted, however, Newton stipulated that an additional force outside the solar system must work in tandem with the gravitational forces inside the solar system. Several modern physicists have acknowledged Newton's alternative, one of them being the Nobel laureate Steven Weinberg. Here is how Weinberg describes it in his 2015 book, To Explain the World.
If we were to adopt a frame of reference like Tycho's, in which the Earth is at rest, then the distant galaxies would seem to be executing circular turns once a year, and in general relativity, this enormous motion would create forces akin to gravitation, which would act on the Sun and planets and give them the motions of the Tychonic theory. Newton seems to have had a hint of this. In an unpublished Proposition 43 that did not make it into the Principia, Newton acknowledges that Tycho's theory could be true if some other force besides ordinary gravitation acted on the Sun and planets.
Weinberg's reference to, quote, forces akin to gravitation, unquote, refers to inertial forces such as centrifugal, Coriolis, and Euler forces. Using Einstein's general relativity as the sanction, Weinberg indicates that, in the view of modern physics, a universe rotating around a fixed Earth will create inertial forces that mimic the force of gravity. As the universe's inertial forces meet the gravitational forces in our solar system, both will contribute to how the Sun and planets will move with respect to each other. Weinberg also notes that the inclusion of forces outside the solar system that will allow the Tychonian geocentrism are specified in Newton's Proposition 43, which was originally planned to be added to page 510, the last page of the Principia. In Proposition 43, Newton says, "In order for the Earth to be at rest in the center of the system of the Sun, planets, and comets, there is required both universal gravity and another force in addition that acts on all bodies equally according to the quantity of matter in each of them, and is equal and opposite to the accelerative gravity with which the Earth tends to the Sun. For such a force, acting on all bodies equally and along parallel lines, does not change their position among themselves, and permits bodies to move among themselves through the force of universal gravity, in the same way as if it were not acting on them. Since this force is equal and opposite to its gravity toward the Sun, the Earth can truly remain in equilibrium between these two forces and be at rest.
and thus celestial bodies can move around the Earth at rest, as in the tectonic system.
Whereas today some physicists wishing to advance heliocentrism seek to confine Newton's physics to the solar system and thereby exclude any external forces coming from the universe, as we noted earlier, this results in having to regard inertial forces as fictitious, mere effects that only appear when objects are accelerated, as we saw in the amusement ride when people are held fast to its spinning wall. Conversely, by expanding Newton's mechanics to the rest of the universe, which, in Newton's case, means that his absolute space will rotate around a fixed Earth, the inertial forces created by the rotation are real forces that are caused by the mass in the universe. In other words, they are forces that actually cause things to accelerate rather than being merely effects of acceleration. In this way, the universe's inertial forces contribute to the movement of everything from the revolutions of the celestial bodies to the directions of hurricanes on Earth and the turning of the Foucault pendulum. Inertial forces will likewise pull the planets around the Sun and pull the Sun and Moon around the Earth. As noted in Newton's Proposition 43, all of these movements are permitted by Newton's physics and confirmed by modern physics. In fact, having real inertial forces is better for Newtonian physics, since without them, Newton never possessed a physical explanation for what causes the planets to continue to accelerate around the Sun without eventually being pulled into the Sun. In addition to Newton's Proposition 43, allowing a geocentric universe, his mechanics also show that the Earth will have no inclination to rotate. When the gravitational and inertial forces are balanced around a center of mass, they cannot generate a torque, and thus the Earth will remain absolutely motionless. This state of rest is calculated in the above equation. If the reference point R is chosen so that it is the center of mass, then the resultant torque, T, is zero. Because the resultant torque is zero, the body will move as though it is a particle with its mass concentrated at the center of mass. By selecting the center of gravity as the reference point for a rigid body, the gravity force will not cause the body to rotate, which means the weight of the body can be considered to be concentrated at the center of mass. In other words, not only will the Earth remain at the center of mass, there will be no torque to make it rotate with the rest of the universe.